So when I take a look at this first one that I had, for me, I'm always hoping if I'm going to have something with x squared, that it's going to factor. And it might. But the first step that I'm going to do is to distribute everything out. So when I distribute this out, I'm looking at 12 minus 3x minus 4x. So that's minus 7x. And then negative x times negative x would be plus x squared. And then I've got minus 6. Personally, if I'm going to factor this, I want that x squared to be in the front. And I'll group my constant. So 12 minus 6 would leave me a positive 6. And what do you know? I give us something to factor. But if you don't see how to factor it, that's okay. Just reach for the quadratic formula. No one's testing you on your factoring skills. You do have to be able to solve a quadratic equation using some tool. So this ought to factor as x minus 6 times x minus 1, which means that my final answers are 6 and 1. This one, I gave us a decimal, but if you don't like decimals, you can change it to a fraction. Either way, I'm going to start off in the same place, meaning distributing that negative x through. So I'd have negative x plus x squared and then minus 0.75. Now at the moment, that's looking a little bit gross to me, but I am going to rearrange it. And pause here for a second. So this is the point where it's really up to you. If you don't like decimals, I would choose to change the 0.75 to a 3/4. If you're going to plug it into the quadratic formula and use a calculator anyway, then I would say it doesn't matter. You might as well leave it as a decimal. But if we're going to try to do this by hand, for me, I would rather change that to 3/4. Now, personally, the reason that I want to change it to 3/4 is because then I can multiply the entire equation by 4 and not have to deal with fractions at all. So I'd be looking at 4x squared minus 4x minus 3 is equal to 0, and then thinking about how can I factor that. And we can factor, or again, just stick it into quadratic formula. But I know with that negative 3 out there, I'm going to end up having a 3 and a 1. And one of those two is going to need to be negative. Then I'm looking at the 4x squared. And there are two different ways that I can factor that, as a 2x times a 2x or a 4x times a 1x. And then it just kind of comes down to plugging the numbers in and playing around with it. So if I tried 2 and 2, then when I distribute that out, I'd end up with a 6x and a 2x. And I can use a 6 and a 2 to get a negative 4. So it looks like my 2x and 2x are going to work. I just have to be careful about which one is negative. I need my negative 6x term and a positive 2x term to end up with, in the end, a negative 4. I'm going to pause. No one's asked any questions. I went through all of that super quick because, again, if you were doing this problem on homework, you could just stop right here, plug things into the quadratic formula. If you had to do it by hand, this is personally how I would do it. So I'm looking at one x value of 3/2 and another x value of negative 1/2. Just for fun, would anyone like to see me use the quadratic formula instead? Cool. So let's go ahead and work through this problem with quadratic formula also. I'm going to erase this other one. And move my chair out of the way because it's really annoying. So to use quadratic formula on this, I'm probably just going to take it straight from here. So as a refresher, if somehow you have made it this far without memorizing the quadratic formula, the time has come. if I have ax squared plus bx plus c is equal to 0, then our quadratic formula says that x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. There are happy little songs you can use to memorize this. But heck, you get a sheet of notes. If you really don't remember the quadratic formula, put it on your notes. So to use that here, negative b, so I'm looking for the term with just the x, and in this case, the just x term has a -1 for a coefficient, so I'd have -1 plus or minus the square root of 1 squared minus 4 times a is an invisible 1, and c is -0.75. And that whole thing is divided by 2 times 1. So if I start cleaning that up, negative, that's going to become a positive 1, plus or minus. Now inside the square root here, 4 times 0.75, that's going to be a 3. And since I have minus a minus, we'll be adding 1 plus 3 inside, which is very convenient because 1 plus 3 is 4. Square root of 4, nice number. I'm looking at a 2. So I'd have 1 plus or minus 2 all over 2. And from there, to get our 2 actual answers, I'm going to split that into 2 fractions. So I'm going to think about that as 1 plus 2 over 2 and 1 minus 2 over 2, or 3/2 and -1/2. So we get the same answers that we got over here from factoring. For me, factoring is faster. For you, quadratic formula might be faster. Either one is totally fine, full credit either way. Well, let's make sure that our multiplication is going to work here. So I'm looking at a 2 by 2 times a 2 by 1. My inner dimensions match, and the outside dimensions tell me that the size of my answer should be a 2 by 1 vector. So to do our multiplication, I'm going to have 3 times -1. So that's -3 plus 1 times 2. And -2 times -1, that's a +2. Plus 0 times 2 is 0. So our result is -1, 2. That was weird. We took a matrix A. We multiplied it by some vector x, and we got the same vector x back. Let's make sure that this isn't some weird magical matrix where whatever you multiply it by, you get the same thing back. So I need 2 random numbers. So you can type them into the chat. I got a 5 and an 8. So 5, 8. So here's my matrix A. Here's some new vector. I need a new letter, so I'll call it Y. Here's my matrix A times Y. Practice a little multiplication. 3 times 5. Also, thank you for choosing numbers that are kind of small. So 3 times 5, I got 15 plus 1 times 8. -2 times 5, so -10. Plus 0 times 8. So we get the vector 15 plus 8, what's that, 23, -10. Okay, not some magic crazy matrix. In general, when we take a matrix and multiply it by a vector, we get some totally different other random vector. But for really specific special vectors, When I take the matrix and I multiply it by the vector, I get a multiple of the vector back. In this case, we got a multiple of 1 times the vector back. So when we have that super special relationship, where multiplying the matrix times a vector gives us a constant times the vector back, then we call that constant the eigenvalue. And we call that super special vector that it happened for the eigenvector. To relate this to the worksheet, if I were drawing this thing and I called that y1, no, I call that y0 and I called that y1, then drawing this out, I started with the vector 5 over 5 up 8. I started with that y0 vector. And after I did a times that y0 vector, we got this totally random vector over here that's negative 23 down 10. But when I had this very special vector x0 and I multiplied it by the matrix to get x1, turns out that that super special vector, negative 1 up 2, gave me exactly the same vector back when I multiplied it by the matrix. Isn't that cool? Or totally random, or not totally random because it's math. Okay. I'm going to do one more of these. And multiply by the vector 1, negative 1 really quick. 3 times 1 is 3, plus 1 times negative 1, so plus negative 1, negative 2 times 1, 0 times negative 1, so I get the vector 2, negative 2 back. Now the reason I wanted to show you this one is because that same weird thing just happened. Only multiplying the matrix times that vector didn't give us exactly the same vector back, but it gave us a vector that's twice what we started with. This right here, if I were to draw that out visually, let's pick another letter, let's call that Z. So if that were Z0 and that was Z1, then we started with the vector 1, negative 1. So 1 to the right, down 1. And after we multiplied it by A to get our new vector was exactly twice the length. So it's in exactly the same direction. It's just twice as long. In general, for a 2 by 2 matrix, we expect to have 2 eigenvectors and 2 eigenvalues. That's not always true, but in general, if we're dealing with a 2 by 2 matrix, we're expecting 2 of these special eigenvectors and 2 of these special eigenvalues. So we're going to start with this relationship because this really is what it means to be an eigenvector or eigenvalue, is that this relationship holds. But just like if A and lambda were constants, and I think about I want to try to solve for x, I'm going to move everything onto one side of the equation and factor the x out. So moving everything onto one side, that's going to look like A times X minus lambda times X is equal to 0. Now there's something particular to matrices that's going to make this next step weird, or two somethings. One, multiplication is not commutative with matrices, so it matters which side we factor the X out on. I know usually we think about, or at least I usually factor my X out on the left, but because the X is on the right-hand side of each of these multiplications, and we know that we're talking about vectors and matrices, we have to factor it out onto the right-hand side. Now, the other weird thing about factoring here is I can't just make this A, which was a matrix, minus lambda, which is a number. I can't subtract a number from a matrix, but what we can do is come back up here to this step and say, oh, hey, you know what? When we multiply by the identity matrix, we don't change the problem. It's kind of like we multiplied by 1. And by putting the identity matrix in there, it means that when we factor, we don't have that problem because now lambda times the identity matrix, this is a matrix as well. So now when I do a matrix minus a matrix, we get an answer. There's another subtlety here that I realized. This 0, it's not just the number 0, it's actually the vector 0. When we're talking about a 2x2 matrix, that 0 vector for a 2x2 matrix would be the vector that looks like 0, 0. And because we're talking about a 2x2 matrix here as well, my identity matrix would be the I2 matrix that looks like that. Okay, back to this equation. We talked about this a little bit on Monday, but this right here is some sort of matrix. So if I just give it a new name, like M times that vector X is equal to 0. We talked about this kind of right at the end of class on Monday. If M is invertible, meaning it's non-singular, meaning we can find M inverse, then it means all the critters are dead. If I can find M inverse, then our only solution is that X had to be 0. We don't want all the critters to be dead, or at least I don't want all the critters to be dead. So to keep things interesting, to look for the interesting solutions to this equation, the non-trivial solutions to this equation, we need for M inverse to not exist. And the way we're going to force this M inverse to not exist is we're going to set the determinant of that A minus lambda I, which I was calling M here, equal to 0. And this is going to guarantee that we get the interesting solutions for this equation. So let's see how that plays out. Just trying to decide. Yeah, we'll go with that. Okay. So the matrix that we were just working with in that previous example was 3, 1, -2, 0. I think I got that right. 3, 1, -2, 0. So if I subtract from that lambda times the identity matrix, that means we're taking this identity matrix, and if I do lambda times I2, we would multiply each piece in here by lambda. So that would look like 1 times lambda, 0 times lambda, 0 times lambda, lambda times 1. And if I do that subtraction, with addition or subtraction, the pieces just stay where they are. So I'd have 3 minus lambda, 1 minus 0, -2 minus 0, and 0 minus lambda. And what this is asking us to do is to take the determinant of that and set it equal to 0. Well, when we take that determinant, that's going to be minus. Yes, I always do the sound effect for the determinant. Very important. Not really do it in your head on a test or something, but I think it makes determinants more fun. So I'm going to have 3 minus lambda times negative lambda minus 1 times negative 2 and set that whole thing equal to 0. This is where those quadratic equation skills come into play. Anytime we're finding the determinant of this matrix, we pretty much end up coming down to some sort of quadratic equation and hoping that it factors. So if I multiply this out, I've got a lambda squared negative 3 lambda plus 2. And because I did the problem ahead of time, I gave us something that factored. Isn't that convenient? This factors as lambda minus 2 times lambda minus 1. Which tells me that the two eigenvalues are 1 and 2, which matches what we did just a second ago. So I'm going to put up here somewhere in the corner that our two eigenvalues were 1 and 2. So if we stick with the textbook, then we're going to come back up to this step in the equation. So with this step in the equation, I now have numbers that I can plug in for lambda so that we can solve for x. So at this step of the equation, this matrix right here, if I set lambda equal to, let's do the lambda equal to 1 first. So if I set lambda equal to 1, then this part of the equation is really this matrix here, where I'm plugging in 1 for lambda. I'm going to have 3 minus 1, the 1, and then negative 2. And when I plug in lambda here, I'll have negative 1. So I'm going to have this matrix times this x vector. Now, this is where notation-wise we get to make a choice. I'm going to just choose to label that vector as an x coordinate and a y coordinate. But it would also be totally fine to write that with subscripts. So another common notation would be to write that as x1 and x2. But for me, the subscripts just get a little bit messy when I'm working with it. So I'm going to call it x and y. When we do the matrix multiplication on the left-hand side, we should end up with here 2x plus y is equal to 0. And negative 2x minus y is equal to 0. Whenever you're finding eigenvectors, we should get an infinite number of solutions. Meaning, when we look at these two equations, they should secretly tell us exactly the same information. If I look at that second equation, that says if I added y to both sides, negative 2x is equal to y. And if I looked at the top equation and I subtracted 2x from both sides, that would say y is equal to negative 2x. So they're telling us the same piece of information. And graphically, what that's telling us is that any vector that falls on that line, y equals negative 2x, any vector that falls on this line is an eigenvector. And we can choose essentially any point on that line and call that our eigenvector. So for me, I'm going to choose, I always choose whole numbers, which the book does too. So I'm going to choose to plug in 1 for x, and that would make y negative 2. That is not the only choice. That is the choice I am making. there are an infinite number of correct eigenvectors. Then I'm looking at the matrix right here, but plugging in 2 for lambda. So 3 minus 2 is 1, and another 1, and a -2, and then a -2, times some xy coordinates being equal to 0, 0. We do the matrix multiplication. We'll have x plus y equals 0, and -2x minus 2y is equal to 0. Again, these two should secretly give us the same information. Well, that top equation, if I rearranged it, would say y equals -x. And the bottom equation, if I rearranged it, would look like -2x is equal to 2y. And then I can divide both sides by 2 and have the same equation, which tells me any point that falls on that line is an eigenvector. I'm going to choose to plug in 1 for x, which would make y equal to -1. So that is the other eigenvalue eigenvector pair. 4, 3, 2, 3. So our first step is to find the lambdas by doing the determinant of a minus lambda I and setting that equal to 0. After you do a bunch of these, you can probably skip the step of writing out the minus the matrix with lambdas on the diagonal, because you can probably skip to just sort of doing that part in your head. So our determinant of a minus lambda I looks like the determinant of 4 minus lambda, 3, 2, and 3 minus lambda. We're going to set that equal to 0. You might recognize this equation from our warm-up problem. When I take the determinant, I've got minus. So 4 minus lambda times 3 minus lambda minus 2 times 3 is equal to 0. And we already solved this in the warm-up problem, so I'm going to jump straight to our answer. And ... After you solve that, we're going to get 6 and 1. So these are my two eigenvalues. Next, we can move on to finding the eigenvectors. So let's choose, and in general, we have to do this twice, once for each eigenvalue, but let's choose to start with the lambda is equal to 6. So if I start with lambda equal to 6, then I'm going to plug in 6 to the a minus lambda I matrix. So here it is right here, and we're plugging in 6 everywhere we have a lambda. And that's going to make our matrix look like 4 minus 6, that's -2. Got a 3, a 2, and 3 minus 6 is -3. And that multiplied by xy needs to be equal to the 0 vector. When we distribute that out, I've got -2x plus 3y is equal to 0, and 2x minus 3y is equal to 0. If you trust me, even if you don't, these two equations are the same. The top one, I can add the 2x over. The bottom one, I can add the 3y over. Either way, we're getting that 3y is equal to 2x. We get one piece of information out of two equations. So if 3y is equal to 2x, then to find the corresponding eigenvector, we can choose any number for x and then figure out what the y value has to be. You can always choose to plug in 1 for x, It just might give you fractions then when you solve for y. That's okay. Alternately, you can choose numbers so that they work out to be whole numbers, which is always a little friendlier to think about if this is a biological context. I don't like to think about thirds of bunnies or something, but I'll keep it simple. If we plug in 1 for x, then the corresponding y value would be 2/3. Also acceptable is any number times this vector right here. So there's a great question in the chat about will the equations always be the same? And I've been really careful about this to state that they'll always give us the same information. There's a theorem, and we're going to get to it in the next section, that says if the matrix meets certain criteria, then yes, these are always going to be the same. What I would say is as long as you get 2 separate eigenvalues, then these will always be the same. Sometimes, if you think about like solving a quadratic equation, sometimes you get a repeated root, meaning if we did this and the quadratic equation part came out to look like, I don't know, lambda minus 3 squared is equal to 0, where we're really only getting 1 eigenvalue. When that happens, your 2 equations will not be the same. Okay, and that was probably more information than you wanted. Eventually, I'll try to work in an example where that happens. But for now, these are usually going to be the same, and they'll always be the same as long as you got 2 different eigenvalues. So line 3y equals 2x or y equals 2/3 x, then that's looking like 3 up 2. That's this line right here. And the point 1 2/3 is on that line. Right, this is my y equals 2/3 x. And the point 32 is also on the line. So any point that's on that line does represent the coordinates for an eigenvector. Since I've got this stuff up here, let me just graphically bring this back around to that worksheet and say, if I were thinking about 1 2/3 as if this is my eigenvector, then graphically, here's my eigenvector. So I'll call that V0. And if A times V0 is equal to V1, then that V1 should be 6 times this vector, or this vector, but 6 times as long. And my V1 would look like that. So it would point in exactly the same direction. It would just be multiplied by 6. Let's go ahead and find the vector that corresponds to lambda equals 1. So we're going to repeat the process. I'm going back to this matrix right here. But now for lambda equal to 1, that matrix would look like 4 minus 1. So that's a 3 and a 3 and a 2 and a 3 minus 1 is also a 2 times xy. Oops, I missed my equal sign. is equal to 0, 0. So if I write that out, that's 3x plus 3y is equal to 0, and 2x plus 2y is equal to 0. So they are, in fact, the same equation again. Both of these are saying y equals negative x. So I can choose my eigenvector by picking any point on that line. I'm going to choose -1 for x, which would make y +1.